Hello everyone, this will be a video to talk about the method of solving quadratic equations using square roots, and also to review simplifying square roots, which is part of that process. Okay, so first of all, on the right, here's three different examples of square roots, and none of these are fully simplified. So there are three things to check for to make sure square roots are simplified. The first, you want to check to see that there are no perfect squares inside of a square root. So you may recall a perfect square is just some number that's been squared. So for example, 2 squared is 4, so 4 is a perfect square. 3 squared is 9, so that's a perfect square. 1 is a perfect square, so is 0. We could do 16 and so forth. Right, so we want to check these square roots, like square root of 72, and we want to make sure that there are no perfect squares that are factors of 72. So how do we do that? Well, here's the method that I like. I usually start to make a factor tree and just look for really anything that is a factor of 72. Now the fastest way to do this is if you can think of the largest perfect square that goes into 72. So you may eventually notice that this is 36 times 2, and if you do that, okay, so then we would have the square root of 72 is the square root of 36 times the square root of 2, and then 36 can be square rooted, okay, and we can't do anything else with the square root of 2 because that's a prime number and there are no more perfect squares that are factors. So this would simplify, and then you would just remultiply those two things. You would have 6 square root 2 would be the simplified version. Now let's say you didn't see that 36 was a factor of 72, so you can still get there using different combinations of factors. So let's say you knew that this was 9 times 8. Okay, so square root 9 times square root 8. 9, the square root of 9 is 3. And then square root 8 can be broken down into square root 4 times square root 2. And then square root 4 is 2. And so now you have 3 and 2, and we can't do anything else with the square root of 2. So now you would remultiply all of those, and you would get the same thing. You would have the 3 times the 2 is 6, and then square root 2. Alright, a second rule for simplifying square roots, in addition to making sure that we have no perfect squares as factors, we also want to make sure that there are no fractions inside square roots. So on the right here we have the square root of 5/4, and that's not considered to be simplified because it's a fraction inside a square root. So the way to deal with this is to break this up. We have a quotient rule for square roots, and it basically says that the square root of a fraction is the same thing as the square root of the numerator divided by the square root of the denominator. Okay, so now we have like square roots in a fraction instead of a fraction in square roots. And then we would just see what we can do to simplify each of those square roots. So the square root of 5, that's done. If it was something like square root 72 in the numerator, then we would go through that process that we just did to simplify that. And then the square root of 4 conveniently works out. So we know that the square root of 4 is 2, and then that's fully simplified. A third rule, we want to make sure that there are no square roots in the denominator of a fraction. Right? So watch what happens here when I try to simplify the square root of 3/7. So this one, I can't leave it like this because it is a fraction in a square root. So I'm going to do the same thing I just did on the last example. So this would be the square root 3 over the square root 7. And now I still have a bit of a problem because I can't square root 7, I can't square root 3, but this is not fully simplified because there is this square root of 7 in the denominator. So when this happens, we need to do what's called rationalizing. So right now the denominator is an irrational number. The square root of 7 is irrational, and I need to make it rational. So the way to do that is you take whatever it is that you're trying to simplify, and then we're going to multiply by a version of 1, okay? And I'm just, whatever this square root in the denominator is, that's what I'm going to use in the numerator and denominator of the fraction I'm multiplying it by. All right, so in other words, you're just going to multiply by a square root over a square root and just match whatever's in the denominator. All right, and then you would multiply straight across like with other types of fractions. So in the numerator, square root 3 times square root 7 is square root 21. And in the denominator, square root 7 times square root 7 is the square root of 49. And the square root of 49 is 7. So if you want to maybe remember this as a rule, this is true all the time. If you have a square root times itself, that's always just going to be the number inside the square root without the square root sign. Alright, and then lastly we would check like square root 21 and make sure that it's fully simplified. So sometimes when you multiply you get things, like 72 that we could do a little bit more work to simplify. However, I already know that 21 is 3 times 7. Those are both prime numbers, so I know that the only way I can really break this down would be square root 3 and square root 7, and I can't really do anything with either of those two. So if you happen to notice that you're multiplying primes to get this numerator, then you can be sure that this is fully simplified. Alright, let's do one more example, maybe a few. If we had the square root of, how about 10, we'll do 10 sevenths. Let's do something different than 7. How about 10 elevenths? Okay, so first thing I would do is split this into a square root in the numerator and a square root in the denominator. So that way at least I don't have a fraction inside the square root. Now square root of 11 can't be simplified, but it's still a square root in the denominator, which we don't want. So I'm going to go through that rationalizing process. So I'm going to multiply by square root 11 over square root 11. Okay, so you just match whatever's in the denominator. And then multiply straight across. So you would have square root 10 times square root 11 is square root 110. And then in the denominator, this is going to be square root of 121, which is 11. Now the numerator, can this be simplified? So I'm going to think about what I multiplied. I know that this breaks down into square root 10 and square root 11. And 10 does break down into square root 2 and square root 5. But now all I have are square roots of prime numbers, which can't be simplified. So there's nothing I can do. There are no perfect squares, in other words, that I could factor out. So the final answer, fully simplified, is square root 110 over 11. Alright, and let's work on something like 3 over square root 6. Okay, so first of all, there are no perfect squares in the square root because square root 6 is just square root 2 times square root 3, and those are prime numbers. There are no fractions inside square roots, but there is a square root in the denominator, so I need to rationalize this. So I'm going to multiply by square root 6 over square root 6. Now in the numerator, we just smush those two together. The 3 does not go inside the square root, and the 6 does not come outside, so this would just be 3 square root 6. In the denominator, we'd have square root 6 times square root 6 is 6. And then there's one more step that can be done. If you can reduce things that are outside the square roots, you would do that. So both 3 and 6 can be divided by 3, so that's going to become 1 square root 6 over 2. Okay, so I crossed out a 3. And then that's the final answer. Now I can't divide 6 by 2 because the 6 is in the square root and the 2 is outside, so that's another rule. Alright, so that describes how to simplify square roots, and then let's go on and look at a few examples of solving by square roots. So here's an example, and then this is a part 2 of something we've talked about before. So basically your process for solving by square roots, we talked about converting first into vertex form. Right, and remember that's a times x minus h squared plus k equals something. And in this case, since we're solving, we're not going to have a y on the other side, it's going to be a 0. So, all right, so we want to put that in vertex form, and then you would go through the process of getting the thing that's squared by itself, and then we would square root both sides of the equation. Okay, so let's look at 9x squared minus 25 equals 0. Now you could think of this as either in standard form or in vertex form. In standard form, this would be like 9x squared plus 0x minus 25 is 0. But I could also think of this as being in vertex form. So this would be like 9 times x minus 0 squared minus 25 equals 0. All right, so how do you know which to go with? Well, in this case, it's more convenient to think of it in vertex form. And basically, anytime you have a quadratic equation that doesn't have the x term to it, okay, or if it's just a 0x that we're not seeing there, then you can think of those equations as if they were in vertex form. So that being said, I just want to start in and get the squared part by itself. All right, so we would start by adding 25 and then dividing by 9. All right, so notice only the x is squared in this equation. The 9 is not part of the thing that's being squared, so that needed to be moved as well. Okay, and then now I'm going to square root both sides of the equation. All right, and right away here I would put in a plus or minus sign, because when you're solving squared equations, there are always two solutions. So, for example, if we had x squared equals 25, then I know that x could either be positive 5 or negative 5. But you're going to lose that negative solution if you don't put that negative sign in at some point. Okay, so we have x equals plus or minus, and then I need to simplify square root 25 over 9. So I'm going to think of this as square root 25 over square root 9. And then this one simplifies nicely. This is plus or minus 5 over 9. All right, here's a second example, and this one is not in vertex form, and I can tell that because there is an x term. Okay, there's a 2x, not just a 0x. So first I need to put this in vertex form. So first of all, it is in standard form. It's equal to 0. I can identify a, b, and c, and then I'm going to use the equations to try to find h and k. So we have h is b over negative 2a, and k is c minus a h squared. All right, so h is 2 over negative 2 times 5. And those 2's will cancel, so this is going to be a negative 1/5. And then k is c, negative 7, minus a, which is 5, times h squared, so negative 1/5 squared. And that's negative 7 minus 5 times, and then I would leave this as a fraction. I think it's easier to square rather than decimals. Or you could just enter the entire thing on a calculator. But if you're doing it by hand, this is what I would do. So negative 1/5 squared, right? Negative 1 squared is 1, 5 squared is 25. And then multiply, so negative 7 minus, and then that 5 can cancel in the numerator and denominator. So that's going to be minus 1/5. And then get a common denominator to subtract that. So negative 7 would be negative 35/5 minus 1/5, and that's negative 36/5. Right. Now, for solving with square roots, I would leave the h and k as fractions as well. So let's go through the rest of solving, and then I think you might see why it's a little bit more convenient, particularly with k, to have k as a fraction. So next I'm ready to write this in vertex form. So I have a is 5 times x minus -1/5, so that's going to be a plus, squared, and then plus k, so plus a negative 36/5, and that equals 0. Alright, so next we want to get the square root, or I'm sorry, the squared part by itself. So the first thing to do is add k to the other side. And then we will divide by 5. Okay. Now on the right, if I divide by 5, okay, that's a little bit messy, so I think what I'm going to do instead is choose to multiply by 1/5. Okay, so divide by something or multiply by the reciprocal. And then we end up with x plus 1/5 squared. And then this is going to be 36 over 25. And then we're ready to square root both sides and put in a plus or minus sign. And we have x plus 1/5 is plus or minus. And now see how nicely this works out because I left this as a fraction. So it turns out that we can square root numerator and denominator. So this is going to be square root of 36 is 6, and square root of 25 is 5. So we have x plus 1/5 is plus or minus 6/5. And now we want to subtract 1/5 to get x by itself. And that always goes in front of the plus or minus sign. Alright, now if we had a square root here where we have the 6/5, this would be probably close to a final answer. But since both of these are fractions without square roots, they can be combined, so the simplest form would be to actually go ahead and add those fractions. So we have two answers. We have, first of all, -1/5 plus 6/5, and then we also have -1/5 minus 6/5. So the only sign changing is the one in the middle. This 1/5 is going to be negative in both cases. So your first answer is 6/5 minus 1/5. That's 5/5 or 1. And then the second answer is -7/5. So one more thing to notice about this, you don't always have two answers that look exactly alike, just with one plus and one minus. So be careful about doing this. So a lot of times I'll see students solve one of these and get maybe like -7/5, and then they'll assume that the other answer is +7/5. But you can see that that's not always the case. Alright, here's one more example, and this one also is not in vertex form. I can see that because there is an x term. So I'm going to start out by finding h and k. So h is b over -2a, which is 56 over -2 times 1/12. And that simplifies to be -1/4. K is c minus ah squared, which is -41 minus 1/12 times -1/4 squared. And this is -41 minus 1/12 times 1/16. And then 1/12 divides, 16 evenly divides 1/12. So this is going to turn into -41 minus 7, and that's -48. So we have h is -1/4, k is -48. So now we write vertex form. So we would have a is 1/12 times x minus -1/4 squared plus k equals 0. And then we start solving. So add k to the other side. And then divide by a. So divide by 1/12. Alright, now 48 over 1/12 can be simplified. So I'm going to go ahead and do that now as well. and 48 and 112 can both be divided by 16, so that's going to leave 3 and 7. Okay, and then we square root both sides. So we would have x plus 1/4 equals plus or minus the square root of 3/7. Okay, so square root both sides. And then we have two more things to do. I need to get x by itself by subtracting 1/4. That goes in front of the plus or minus sign. And then I also need to see if that square root is fully simplified. So I have a fraction inside the square root, so it's not. So I'm going to make that plus or minus square root 3 over square root 7. And then I still have a square root in the denominator, so I need to rationalize that. So I'm going to multiply by square root 7 over square root 7. We've done this one before. So that's negative 1/4 plus or minus square root 21 over 7. All right, and then 21 is 3 times 7, no perfect square factors in there, so this is as simple as it gets. All right, so some of your answers will be left like that with square roots and the plus or minus sign. Other times, like in the previous example, you may be able to keep going and get to fractional or even integer answers. And then one other comment here, answers like this previous example, if you get integers or fractions, that's a sign that this could have been solved by factoring as well. But if you get answers that are square roots that can't be simplified, then that's an indication that we could not have solved this by factoring. Okay, so that's the general process. So we've gone over 3 rules for simplifying square roots and then how to solve using square roots. And we did one example where the equation was already in vertex form, and then 2 examples where it was not, and we needed to convert it into vertex form first.